So now we are going to use the um, vector addition or subtraction to find an acceleration in two dimensions. All right, so let's recall what the definition of the acceleration is. So the acceleration is delta v, the change in velocity over time, right? Or is equal to v final minus v initial over delta t. So in order to find the acceleration, we have to find the difference between the final and initial vector. So pretty much we have to find first step, find delta v, which is vf plus the opposite of vi. And then step two is dividing by delta t, whatever that is. All right. So recall that if in general, how do I find the components of a negative of a vector? If vix and viy are the components for vi, then negative vix and negative viy are components for negative vi. All right. So the best thing to do here is we can draw it as well, just to visualize it. But remember, when you do component method, you don't really need to. So here's an example. It says a car turns from a road into a parking lot and into an available parking space. It doesn't matter. The car's initial velocity is 4 meters per second, east 45 degrees north. Usually we don't put the angle if it's 45 degrees. And the car's velocity just before the driver decreases speed is still 4 meters per second, but now is east 10 degrees north. And all this maneuver, it takes 3 seconds. And we want to calculate the acceleration of the car during the turn. All right, so if it helps us, we can draw a little bit a diagram just to see what it looks like. So let's see what is given to us, first of all, numerically. We have initial velocity to be 4 meters per second, east north. I'm not writing the angle because it's obvious. And the v final is still 4 meters per second, but now is east 10 degrees north. As you can see, by the way, the time for all this turn is 3 seconds. So we have, by the way, two significant digits that we have to report, right? And what is required to find from us is the acceleration, right? So if I were to do the standard form, the analysis, I need to use the equation acceleration equal to delta v over delta t. And I know that delta v is v final minus v initial, right? So first I have to find that, the delta v, and then I have to divide it by delta t. So let's just draw a quick diagram here. What does this look like? All right, so this is north, this is east. So the car initially is here, and it has a velocity of 4 meters per second, right? And is going on that direction, 45 degrees. And then it's turning. So my guess is it's turning this way. And eventually, somewhere here, it has this direction. So remember, this line here represents the actual path, right? And these are velocity vectors. So now it's still 4 meters per second, but now this is only 10 degrees. So this is initial velocity, and this is final velocity. So all this is just for us to make peace with it, to say, okay, what is going on? How is this motion happening? But in terms of vectors, we absolutely don't care. We don't even need to know physics. All we have to do is just use our component method, right? So we're going to use component method to find our vector. So again, if I were to just care about the vectors, here is vi. This is roughly, so I'm just putting the compass directions. This is, I'm just putting both vectors in the same place. This is VF, all right? And what we're looking for is, this is negative VI. Those are looking for delta V, right? Which is this one here. All right, so I know it looks like a little bit messy here, but this is delta V. And again, just FYI, you don't really have to draw this. But the component method, right? So we have VF, the vector, we have negative VI that we have to add, and we want to find delta V, the change in velocity. All right, so both our vectors are on the first quadrant, however, VI will become negative, right? So the X and Y component. So VF is, once I find them, the components, so is, here, let's draw the diagram. It's something like this, right? So this is 10, this is 4, this is X, and that's Y component. We have 3.94 for the X component, meters per second, and 0.69 meters per second for the Y component. And we do the same for the VI. We find the components and then we negate them. We put a negative sign in front. So it's negative 2.82 meters per second. Because remember, we're not finding the components for VI, but for negative VI, which is like this, right? And this is the X, and that's a Y. All right? So they're both negative. Since it's 45 degrees, they're both the same. Okay, and at this point, we just add them, the same as we do with components. So this is plus 1.12 meters per second, and this is negative 2.13 meters per second. All right, at this point, so this is delta Vx, this is delta Vy. As you can see, the positive and the negative tells us that we are somewhere in the east quadrant, right? Well, let's find it exactly. So first we find delta V to be its magnitude to be square root of 1.12 squared plus minus 2.13 squared. So delta V is approximately 2.41 meters per second, and the angle is inverse tan of 2.13 over 1.12. No units, obviously, so theta is approximately equal to 62.3 degrees. If you put the signs, you get a negative 62.3 degrees, which tells you the fourth quadrant or the southeast, right? But we know that already. So we can report the delta V as a vector to be roughly 2.41 meters per second, and the direction is east, 62.3 degrees south. At this point, we can actually find the acceleration. Remember, is delta V over delta T. So the acceleration is approximately 0.8, two significant digits, meters per second squared, meters per second, and the direction is east, 62.3 degrees south, right? So if I were to report it on a scientific notation, the acceleration is approximately 8.0 times 10 to the power of negative 1 meters per second squared, east, 62.3 degrees south. So here is how we use component method to find acceleration in two-dimensional motion. All right, the textbook has some more example. I took this from the textbook, and you can do more from textbook. All right.